Second derivatives and stationary points, example 1. Now this is just to illustrate what we were saying about d2y dx squared being equal to 0. So y equals x squared. So if we differentiate that, dy dx is 2x. Now for any of the stationary values, we need dy dx to be equal to 0. So 2x is equal to 0 means x is equal to 0. Now differentiate again d2y dx squared. That's going to be equal to 2. Now that is definitely positive when x equals 0. From what we said before, positive implies that we have a minimum. And indeed, y equals x squared, you should know what that looks like. It looks like this, and it has a minimum. Let's try and do the same thing with x cubed. So dy dx is equal to 3x squared. Let's put 3x squared equal to 0. Once again, that means that x equals 0. It's the only solution to that. Let's do the second derivative, d2y dx squared. That's going to be 6x. And d2y dx squared, evaluated when x is 0, is then equal to 0. Now, as it happens, y equals x cubed does indeed have a horizontal point of inflection at the origin. But if we consider y equals x to the 4, dy dx is equal to 4x cubed. Put 4x cubed equal to 0, and the only solution is x equals 0. If we do the second derivative there, that gives us 12x squared. And therefore the second derivative, evaluated when x is equal to 0, is 0. But if we draw y equals x to the 4, it's a similar sort of shape, 2x squared. It's not quite the same shape, it's not a parabola. It's much flatter at the bottom and much steeper up the sides here. But it has a minimum. So we have a second derivative being 0, but we have a minimum. And that's the problem. The second derivative being 0 tells us nothing. We could have any of the types of stationary point. And that's why if you come out with the second derivative being 0, you should then use a sine graph. However, if you get a situation like this, where the second derivative is positive, then you definitely know that you have a minimum. If it comes out to be negative, you definitely know you have a maximum.